In the interim, the occasion skyline of a dark opening is the point in space where nothing can get away, and it is fundamental to grasping the nature and impact of dark openings in reality. Both act as achievements denoting the cutoff points of time. We can't notice any occasions happening past these skylines. Occasion skylines and the limits of the universe are not by any means the only components of geodesic deficiency. If we consider other complex principles, we find another captivating similitude between the peculiarity at the focal point of a dark opening and the peculiarity just before the Big Bang. Both are particular points with limitless density, occupying the entire space. The primary difference is that the peculiarity of the Big Bang exists before and encompasses the entire space, while the peculiarity of a dark opening exists in the future, within the entirety of dark opening space. If you find this part hard to comprehend, let's dive deeper into geodesic deficiency to enhance your understanding. According to the theory of general relativity, objects not affected by forces will follow something known as a geodesic. In Riemannian math, a geodesic is the most direct path between 2 points on curved space with irregular shapes, such as an inward or outward curved space. In a circle, geodesics form a system that defines the shape of spacetime. They will extend vastly unless they are forced to end at some point. According to this theory, all geodesics will continue indefinitely, except at certain points. This state is referred to as geodesic deficiency. Geodesic deficiency refers to the situation where a space has some geodesics, or shortest paths between 2 points, that can't continue indefinitely but must end at a finite point after a limited time. It is often associated with the presence of a region in spacetime where geodesics can't proceed endlessly but exist only for a limited period or end at a specific point, such as a peculiarity. This can happen when spacetime has uneven curves and is affected by an extraordinarily powerful gravitational force. In the theory of general relativity, singular points are defined as the endpoint of geodesics. All geodesics in the universe come together and end at the Big Bang. We call the Big Bang a peculiarity because it represents the endpoint of spacetime in the past, as it occupies the entire past spacetime. A dark opening contains a peculiarity, like a spacetime point in the future. It has the inverse direction compared to the model of the universe's origin, according to the theory of the universe's origin. This is the second similarity I want to share with you. Geodesics in the spacetime of a dark opening may also end at the peculiarity in the future. It is a process in which matter is completely separated and compacted at the peculiarity. Considering that a dark opening is a limitless entity, the question of whether you will be crushed by a dark opening remains unanswered. The peculiarity of a dark opening is the future endpoint that involves the whole spacetime under the event horizon, just like how the Big Bang is the past endpoint that includes everything outside. When comparing the two shapes, you may see that they are nearly identical, with the only difference being their direction. Dark openings point toward the future, while the Big Bang points toward the past. Dark openings are like little universes implanted inside a larger universe. They are regions where the gravitational force is so strong that not even light can escape, creating an event horizon beyond which nothing can return. The universe we observe could, in a similar way, be embedded inside a much larger structure, perhaps a dark opening in another universe. The string theory, while theoretical, offers an interesting alternative to the traditional theory of the Big Bang. It suggests that our universe could be part of an eternal sequence of universes, each born from the remnants of the past one in an everlasting cycle. This idea aligns with the nature of dark openings, where matter falls to a limitlessly dense point, potentially creating a new universe inside. The similarities between the singularities of dark openings and the peculiarity of the Big Bang are compelling. In both cases, we are dealing with points of infinite density where our current understanding of physics breaks down. Geodesic deficiency explains this concept in general relativity. A geodesic is the shortest path between 2 points in curved spacetime. Geodesics continue indefinitely unless they encounter a peculiarity, a point where the conditions of general relativity no longer hold, and infinite curvature occurs at these singularities. All paths end at the Big Bang. This peculiarity exists before, representing the beginning of our universe. For dark openings, the peculiarity lies in the future, at the center, where all matter falling into the dark opening is eventually crushed to a boundlessly dense state. This duality suggests a significant connection between the beginning of our universe and the nature of dark openings. Another interesting perspective is the cosmic microwave background, CMB, radiation. The CMB is the remnant glow of the Big Bang, the thermal radiation left over from the early universe, now seen as microwave radiation. It provides a snapshot of the universe when it was just 380,000 years old, offering crucial evidence for the Big Bang theory. The CMB is uniform in all directions, indicating that the universe was once in a hot, dense state before expanding and cooling. The CMB and the event horizon of a dark opening both act as boundaries in our understanding of the universe. The CMB marks the limit beyond which we can observe, as light from farther away has not had time to reach us since the Big Bang. Similarly, the event horizon of a dark opening marks the point beyond which nothing can escape, not even light. These boundaries highlight the limits of our observational abilities and our understanding of space-time. They suggest that there may be more beyond these horizons that we cannot currently see. This idea aligns with the concept that our universe could be a part of a larger, more complex structure, potentially a dark opening in another universe. The universe, to sum up the grandiose string hypothesis and the idea of dark openings, offers intriguing bits of insight into the nature of our universe. They propose that our universe may be part of an unending pattern of creation and obliteration, with every universe arising from the remainders of the past one. The similarities between the singularities of the Big Bang and black holes, alongside the limits checked by the CMB and event horizons, suggest that our universe may be embedded within a larger structure, potentially a black hole in another universe. This viewpoint challenges our understanding of space-time and the universe, opening up additional opportunities for exploring the significant secrets of the universe. What if the universe was not a huge rubber ball, but rather a colossal black hole with a span of a huge number of light years? We've struggled for a long time to understand where this turbulent and exceptional mass of matter comes from. In this video, I believe that you should relinquish natural principles and hypotheses, because, truly, humanity is on the edge of finding answers to the most convoluted questions. The Big Bang Theory may be inaccurate, and we may be just a bit of matter inside a massively huge black hole. Join us on a thrilling journey as we explore a grand question: could people truly exist inside a black hole? This is I2200M, a scientific channel diving into the significant secrets of the universe. The idea that our whole current universe is a peculiar entity deep inside a black hole might sound a little insane, but it's not completely unwarranted. Returning to the time before the Big Bang, quantum physics suggests that all the matter we see today was packed into a substance with endless density, similar to a singular point inside a black hole, which we can now analyze. Scientists have a clear picture of the early universe, known as the theory of prehistoric cosmic detonation. In this model, quite a while ago, the universe was much smaller, hotter, and denser than it is today, around 13.8 billion years ago. During the early stages, everything that makes up who we are today was formed in the initial seconds of the universe's existence, all from a small, reduced ball with infinite density, roughly the size of a peach, and a temperature of more than 1,000,000 trillion degrees. The possibility of a universe emerging from nothingness might sound extremely unrealistic, but the evidence for it is very convincing. Galaxies are moving away from one another, like bits of shrapnel from a detonated shell, and the lingering heat from the Big Bang remains present surrounding us, despite having cooled significantly due to the expansion of the universe. This afterglow doesn't appear as visible light, rather, it exists as microwave radiation, the cosmic microwave background, CMB, which was discovered by radio astronomers back in 1965. Space experts have done everything from observing the extra electromagnetic radiation of the early universe to measuring the abundance of the lightest elements, and they have found that these observations align with the predictions of the Big Bang theory. Supposedly, this is an accurate picture of our early universe. Anyway, the Big Bang picture is still fragmented. There is a missing puzzle piece: the earliest moments of the universe remain a massive mystery. The issue here is that the laws of physics we use to figure out the early universe are a complicated mix of general relativity and high-energy particle physics. However, they can take us up to a certain limit before a breakdown happens. As quantum physicists attempt to dive deeper into the early moments of the universe, the mathematics become more and more tangled. If we try to solve it, the complexity only grows until everything reaches an impasse. Thus, the answer to the question, what was the universe like before the Big Bang, still lacks a sensible resolution. But now, I can present to you a rather engaging speculative solution. Let's embark on a journey back to the time before the formation of the singularity from the Big Bang and investigate what truly happened. We will also explore whether our current universe may be a world inside a black hole. Just relax about questioning the accuracy of the Big Bang. Since we will not be zeroing in on it, rather we will dig profound into the astronomical string hypothesis. The infinite string hypothesis is one of the critical speculations concerning the beginning and advancement of the universe. It proposes that, before the huge explosion, our universe was not a special starting place, but rather part of an endless grouping of universes existing within an unending chain. This hypothesis was proposed by the American space expert and physicist Alan Guth during the 1980s. He fostered this thought to resolve specific inquiries that the theory of the universe's origin experienced, for example, why the universe shows such great balance or why it has a circular shape that implies it isn't contracting due to the gravitational draw of objects. As per the grandiose string hypothesis, prior to the event of the huge explosion, there was no spacetime or universe as we presently know it. Rather, everything existed in a staggeringly small and staggeringly hot breakdown state, also referred to as a peculiarity. At the moment of the huge explosion, an extremely strong event happened called expansion, causing reality to begin extending unexpectedly and dramatically. The expansion period we are aware of went on for a very brief period, something like 10 to the power of -36 to 10 to the power of -32 seconds. After the enormous detonation, during this period, space extended quickly and unexpectedly, making the universe develop very rapidly, prompting the consistency and balance we notice today. It too makes sense of why the universe has a round shape, considering the attractive powers and negative gravity pulling the universe into a round shape during this stage. Anyway, as opposed to halting after some time, like in the conventional theory of the prehistoric cosmic detonation, the grandiose string hypothesis proposes that the extension won't ever end and continues boundlessly. During this development, each new universe is continually and consistently brought forth from the universe before it. Each new universe may have various attributes and conditions, but they always still stick to the overall laws of physics. As indicated by this hypothesis, our universe is thought of as one of these universes in the perpetual chain. Albeit the infinite string hypothesis proposes a succession of universes, each universe exists freely and does not straightforwardly impact or interface with others within our recognizable reach. As a result, we can't straightforwardly notice or connect with different universes in this chain. Alan Guth's hypothesis shares quite a number of similarities with the idea of black holes that we are currently concentrating on. In the two cases, the huge explosion addresses the abnormal place of the universe, and the cycle of making child universes referenced in the astronomical string hypothesis bears striking similarities to what people ponder about black holes in space. While stars and cosmic systems work under the impact of gravitational waves, we know that baffling peculiarities like black holes might conceal more components of space. This is the reason substances beyond the event horizon can't notice the unusual point inside. It's like a black hole restricting comprehension. We might interpret the unusual point by making it difficult to escape. Assuming that an object falls into the region of the event horizon, nothing can keep it from falling inside the black hole. A similar principle applies to our universe. Essentially, the universe extends endlessly and consistently, impelling forward, making everything be unfit to get away from its sweep. When observing it outwardly, we can't precisely decide if the universe is extending or universes are falling toward the abnormal point of this enormous pipe. This situation is very similar to Galileo's tale about whether the Earth rotates around the Sun or the Sun rotates around the Earth. To give more precise proof on this matter, we have the idea of astronomical microwave background, CMB. It's a hypothesis in space science connected with noticing and concentrating on astronomical microwave radiation. The CMB is light produced from the far-off and beginning stages of the universe. It is produced from atoms formed inside the early universe, allowing light to travel uninhibitedly through space. Before that, the universe was a hot, thick plasma that radiated irregular light, but as particles formed, the plasma became more transparent and no longer absorbed and radiated light randomly. The CMB is seen as microwave radiation with an exceptionally low temperature range, around 2.7 Kelvin, which is about -270.45 degrees Celsius. This is the extra light from the earliest time in the history of the universe after the huge explosion, and we can see it every which way across the sky. The limit of the CMB marks the cutoff of the universe, beyond which light can't get away from the closeness between the CMB and the event horizon. Both are limit lines in existence. The CMB fills in as the limit for light in the universe, where light can't escape from the universe but can move freely through space. The event horizon is the limit of a black hole, where space is so bent that nothing can escape beyond it. Both are connected with the extension and design of existence in the universe. Accordingly, while thinking about it outwardly, the possibility that our universe is a world produced inside a black hole is not, by any means, irrational or counterintuitive. Maybe both the CMB and the event horizon assume essential parts in the investigation of the beginning and development of the universe. The CMB is quite possibly one of the main pieces of evidence for the Big Bang model, assisting us with seeing more about the condition of the universe not long after its development.